I'd like to take a minute and go through linear regression. You guys are familiar with the high-low method, which is one option for determining the fixed and variable cost components when we're describing a mixed cost. Linear regression is a better alternative, but it does require some calculations or a tool like Microsoft Excel. Take this example right here. We've got miles driven over here, and we've got cost in total. So as you would expect, when costs increase from, let's say, or miles increase from, let's say, 1,200 to 7,000, you would expect the cost to increase. But what we have is that some of these are variable, some of these are fixed costs. And this data is plotted over here. And you can see that the function, this line that is the best fit, doesn't do a really good job of describing these data points. Now, the high-low method would simply take this lowest item and then this highest and would determine fixed and variable cost using two data points. Linear regression uses all of the data points to find the line that is the best fit, the line that minimizes the sum of the squared errors. So there are three functions I want to show you. Equals slope, and you can see that right up here, equals intercept, and then equals RSQ, R squared. Now, the syntax for each one of these is essentially the same. So if we want to say equals slope, this is going to give us our variable cost. And you can see that Microsoft Excel is already suggesting what does this function do. Returns the slope of linear regression for these various data points. Open parentheses, known y's. Now your y-axis here, this is going to be your total costs. So the known y's are these costs right here, comma, known x's. Well, the x's are going to be this activity, the number of miles. So known x's. So the formula ends up being C5 through C10 are your known y's, your costs, and B5 through B10 are your known x's. And we come up with, no surprise, let me highlight both of these, the same slope that I calculated earlier. Now the formula for the intercept is essentially the same as far as the syntax, with the exception of the word intercept. So same known y's right here, same known x's, and this is giving us our fixed cost, our y-intercept. And you can see on the graph, let's just highlight this. The fixed cost is $278 per period, and yeah, our total cost seems to have around $278 as its starting point. So you might have noticed right here, if you look at this tab color over here, or this tab, that I labeled this as bad, okay? And I purposely did that. I made some data that has a really low R squared. And R squared really is a measure of the goodness of fit. It is a measure of how well will this data, will the function that we come up with, how well will that predict costs at any particular level. Well, as you can see, the function is going to be this line right here. And it really does not do a great job of predicting costs at a particular level, because here the costs are all the way down here, now they're up here, now they're down here again. It's like a ping pong game. And so a low R squared, and by the way, R squared of 1 would be perfect, R squared of 0 would be completely useless, R squared of 0.095, so basically 0.1, is pretty darn useless. Let's go over here to where it says OK. Now, same kind of thing. We're still using the linear regression formulas. But what I did here is I made the data a little better fit. Now our R squared is 0.89. Not too bad. And what you'll see is this line over here does a better job of predicting the data points. It's almost accurate right here and here, almost exact. And it's in the ballpark over here and over here. So it's better. And an R squared of 0.89 is certainly reasonable. You can see that it changes our equation wildly. Now our variable cost is 12.5 cents per mile, and our fixed cost is 14 bucks. If we go to even better, Here's an R squared of 0.99. Okay, almost perfect. You look at the graph, it does a really good job. And then, of course, the fixed and variable components, they're going to be different because I did change the numbers. If I did make a scenario here, I call it perfect. With the perfect scenario, you have no fixed cost, everything is 10 cents per mile, but you do get an R squared of 100%. So what I'd like to just kind of close with is your data points. You can use equals slope to figure out the variable cost per unit. You can use equals intercept to figure out your fixed cost. And then finally use RSQ, R squared, to determine how well this function will predict the data. How well does it explain the behavior of the data? An R squared close to 1 is good, and R squared close to 0 is really bad. Higher is certainly better. Probably looking for, let's say, 90% or above would be desirable. That is linear regression, just a little bit of an overview.